Semigroups and their representations, Lecture 11, Actions and Acts. In the second part of the course, we will talk about various types of representations of semigroups. The general idea of a representation is as follows. Given some algebraic structure, we try to better understand the structure by realizing it via some other algebraic structure of the same kind, which is in some sense easier or which we think we understand better. And such a realization is called a representation. So our main interest in this course is of course in semigroups. So it's natural to ask the question, which semigroups do we think are easier and which semigroups do we understand better? Here are some possible answers. The full transformation semigroup, or the semigroup of all partial transformations, or the symmetric inverse semigroup, or the metric semigroup, so the semigroup of all linear operators on some vector space. So these are some examples of semigroups which we can think of as being easier or more manageable, and we will try to understand other semigroups by realizing them via these semigroups. So these will be our representations. So in this course we will look at two types of representations. A little bit later on we will study linear representations in which we realize elements of a semigroup using matrices or linear operators. But in the few coming lectures we will study representations by transformations, in which we realize elements of a semigroup using transformations or partial transformations of some set. And for this we need to make a choice. We need to choose either total transformations or partial transformations, and the two choices lead to slightly different theories and slightly different results, and we will try to address both of them in the coming lectures. Also note that for inverse semigroups it is very natural to study representations by partial bijections, so using the symmetric inverse semigroup. So representations by transformations are usually called actions. So let's start by defining what a semigroup action is. So let S be a semigroup and X a set. Definition: an action of the semigroup S on this set X is a homomorphism from S to the semigroup Tx of all total transformations of X. Remark: so this is an action by total transformations, and that's the default meaning of the word action. For other actions we will talk about actions with some other modifier. So for example, an action of S on X by partial transformations is a homomorphism from X to the semigroup Ptx of all partial transformations of X. So for example, any semigroup S acts on any set X trivially, where we realize each element of S as the identity transformation of X. So our homomorphism sends the whole of S to the identity transformation of X. A little bit more complicated example: if we fix some element A in X, we can define an action of our semigroup S on X by sending each element S in S to the constant transformation pi A, and that's a transformation which takes the whole of X and sends it to our fixed element A. So this would be another representation or another action of S on X. Next, let us talk about monoid actions. So let M be a monoid and X a set. Definition: an action of M on X is a homomorphism from M to the monoid Tx of all total transformations on X. And that's the default meaning of the word action. Action means action by total transformations. And an action of M on X by partial transformations is a homomorphism from M to the monoid Ptx of all partial transformations on X. So for example, each monoid M acts on any set X trivially, where every element of M is realized via the identity transformation on X. And also remark that if we have a monoid M, we can consider its actions on a set X as a monoid or as a semigroup, and there is a difference. For a monoid action, we need that the identity of the monoid acts as the identity transformation of X, and for a semigroup action, this is not necessary. So in particular, each monoid action is a semigroup action, but not vice versa. Here is the most classical example of an action, and that's a left regular action. So let S be a semigroup. Consider the set X, which is just equal to S. For an element A in S, consider the map lambda A, so that's a left multiplication with A. That's a map from S to S, and its value at an element X in S is defined as A times X. Then, mapping A to lambda A is a homomorphism from S to the semigroup Ts of all total transformations of S. So indeed, lambda AB applied to X is equal to ABX by definition. This is equal to lambda A applied to BX, and this is equal to lambda A applied to lambda B of X, which is lambda A composed with lambda B applied to X. So this is indeed a homomorphism, because composition, that's a semigroup operation in Ts, so we just checked that this map is a homomorphism. And the corresponding action of S on itself is called the left regular action. And if M is a monoid, then the left regular action of a monoid on itself is a monoid action, because the identity element acts as the identity. One can give an alternative description for an action. So let S be a semigroup and X a set. An action of S on X can be described as a map from S times X to X, which is written in the following way. So the pair A, R, A is in S and R is in X, is sent to A dot R. So dot is what represents the action. A acts on R. And the condition which this should satisfy is as follows. A dot B dot R should be equal to AB dot R for all AB in S and R in X. So in this approach, each element A in S is represented by the total transformation sigma A from X to X, which is defined as follows. If we have an element R in X, then sigma A applied to R is by definition A dot R. And so the condition that A dot B dot R is equal to AB dot R is exactly equivalent to the condition that sigma A after sigma B is equal to sigma AB for all AB in S. Another definition, the set X, which is equipped with an action of a semigroup S, is called an S-act. And the warning, then, an S-act is not just a set, but it's a set which is equipped with an action. So it has an additional structure given by an action of the semigroup S on it. Let M be a monoid with identity 1 and X a set. Similarly to our alternative description for the semigroup action, a monoid action of M on X can be described as a map M times X to X, this should be M, which is written as A, R goes to A dot R, which satisfies the following conditions. A dot B dot R should be equal to AB dot R for all AB in M and R in X, and 1 dot R should be equal to R for all R in X. So the point is that we have the first condition, the same as for semigroups, which just says that the product of elements acts as the composition. But then we have the second condition, which says that the identity element of our monoid should act as the identity transformation of X. And of course, the set X, which is equipped with an action of a monoid M, is called an M-act. Next, let us discuss the notion of an effective action. Definition: an action of a semigroup S on a set X is called effective, provided that different elements of S act as different transformations of the set X. Remark, such actions are sometimes also called faithful. Alternatively, an effective action is the one for which the representation map from S to Tx is injective. However, the words faithful and injective also have slightly different meanings, especially if one considers linear representations and categories, so it is good to have a different word to describe this phenomenon. Example 1. If S is a semigroup which has more than one element, then the trivial action of S on any set X is not effective, because all different elements of X are represented by the same identity transformation. Example 2. If S is a monoid, then the left regular action of S on itself is effective. Indeed, if the identity of our monoid S is E, and A and B are different elements in S, then lambda A applied to E is equal to A, so it's A dot E, A times E by definition, and A is not equal to B, and B is lambda B applied to E. And this means that lambda A as a transformation of S is different from lambda B. So different elements give different transformations. So the left regular action of a monoid on itself is effective. However, for general semigroups this is not true. So here's an example. If S is a monoid with a 0 element 0 and 0 multiplication, which means that the product of any two elements in S is equal to 0, and S has more than one element, then the left regular action of S on itself is not effective, since all elements of S act as the constant transformation pi 0. All elements are sent to 0. So that's a transformation which corresponds to any element in S, because the product of any two elements is 0. So we naturally have a question, does such S admit some effective action on maybe some other set? And answer is yes. And here is how to construct it. So for any semigroup S, consider the corresponding monoid S upper 1, which is obtained from S by adding 1, if S didn't have any 1 to start with. Then, for any element A in S, we have the transformation of S upper 1, denoted lambda A, which is given by the left multiplication with A. Lambda A of R is equal to A dot R for any R in S upper 1. And this defines an action of S on S upper 1 by exactly the same argument as for the left regular action, and this action is effective by exactly the same argument as for the effectiveness of the left regular action for monoids, because now we act on a set on which we have the identity element. Consequently, every semigroup admits an effective action on some set. Here are some further examples of actions. Example 1. If phi is a homomorphism from a semigroup S to a semigroup T, then S acts on T as follows: A dot R is equal to phi of A times R, where A is an element in S and R is an element in T. Example 2. If S acts on X, then S also acts on X times X diagonally. So this means that A acts on the pair R, T, giving the pair A dot R, A dot T. So here A is an element in S, and R and T are elements in X. Example 3. If S acts on X, then S acts on the Boolean of X as follows: A acts on a subset Y of X by giving the subset which consists of all elements A dot R, where R is an element in Y. Example 4. The multiplicative semigroup of all positive integers acts on all positive integers as follows: A acts on R by raising R to the power A. Example 5. The semigroup of all transformations of a set X acts on X naturally or tautologically, where each element of the semigroup Tx acts on X as itself. Similarly, example 6, if K is a field, then the matrix semigroup of all n times n matrices with coefficients in K acts on K to the power n by matrix multiplication on the left. Next, let us talk about morphisms of acts. Let S be a semigroup and X and Y be two S acts. A map phi from X to Y is called a morphism or a homomorphism of S acts, provided that for all R in X and A in S, we have that phi applied to A dot R is equal to A dot phi of R. In other words, the following diagram commutes for all A in S. So we have X, and then we can apply A dot to it to come to X, and we can apply phi to go to Y. Alternatively, starting from X, we go to Y by phi, and then from Y to Y we go by at dot blank. So this diagram should commute for any A. For example, the identity map from X to X is a homomorphism from any S act X to itself. Now we can use homomorphisms to define the category of S acts. Let S be a semigroup, and let X, Y, and Z be three S acts, not necessarily different. Let phi be a homomorphism from X to Y, and let psi be a homomorphism from Y to Z. Then, the composition of psi after phi is a homomorphism from X to Z. Consequently, all S acts, together with homomorphisms between them, form a category. And this category is usually denoted by S act with capital A. Next, let us talk about invariant subsets in acts. Let S be a semigroup and X an S act. Definition: a subset Y of X is called S invariant, provided that A dot R belongs to Y for any A in S and R in Y. For example, both the empty set and the whole of X are S invariant subsets of X. Example 2. A non-empty invariant subset of a left regular S act is exactly the same thing as a left ideal. Example 3. If S acts on X, it also acts on X times X. And in the latter case, the diagonal, which consists of all pairs of the form R, R, where R is an element of X, is an invariant subset. We observe that if Y is an S-invariant subset of an S-act X, then Y inherits from X the structure of an S-act by restriction. And also sometimes an invariant subset is called a sub-act. Next, let us talk about the image of a homomorphism. Let phi from X to Y be a homomorphism of S acts. Proposition: then phi of X is an S-invariant subset of Y. Proof: let R be an element in X and phi of R the corresponding element in phi of X. Then, for any element A in S, if we act by A on phi of R, since phi is a homomorphism, this is equal to phi applied to A dot R, and then this belongs to phi of X by definition. And so phi of X, the image of the homomorphism phi, is indeed an S-invariant subset of Y. Conversely, by the way, if Y is an S-invariant subset of X, then, as we just mentioned on the previous slide, Y is itself an S-act, so it inherits the structure of an S-act by restriction, and then we have the natural embedding of Y into X. That's a homomorphism of S-acts. So each S-invariant subset is the image of some homomorphism. Next, let us talk about congruences on acts. So let S be a semigroup and X an S-act. Definition: An equivalence relation ρ on X is called a congruence, provided that the fact that two elements R and T are ρ equivalent implies that A dot R and A dot T are also ρ equivalent. So in other words, ρ is stable under the action of S. So for example, the equality relation is a congruence on any S act, or the full relation, so the relation where everything is equivalent, that is also a congruence on any S act. Example 3, if I is an ideal of a semigroup S, then the corresponding Riesz congruence ρI, so for the Riesz congruence two elements are equivalent if and only if they are equal or they both belong to I. So we have singleton equivalence classes together with I as a unique non-singleton equivalence class. This is also a congruence on the left regular S act. So any Riesz congruence is a congruence on the left regular S act. And in fact, one can weaken the assumption. One doesn't need to assume that I is an ideal. It's enough to assume that I is a left ideal of a semigroup for this to be true. More generally, example 4, if Y is an invariant subset of an S act X, then ρY, which is defined as follows: two elements are ρY equivalent if and only if they are equal or both belong to Y, is a congruence on X. Using the notion of a congruence, we can define the quotient of an act. So let X be an S act, and let ρ be a congruence on X. Then the set of all equivalence classes modulo ρ, so X modulo ρ, inherits the structure of an S act in the usual way. A acting on the class of R is the class of A dot R. So here R overline denotes the ρ class of an element R in X. So the fact that this is well defined follows from the axioms of the congruence, and the fact that this gives an S act follows from the fact that X was assumed originally to be an S act. And then we have a map which sends an element R in X to its class R overlined in X modulo ρ, and this map is a homomorphism of acts. And then we have the first isomorphism theorem. Let phi from X to Y be a homomorphism of acts over some semigroup S. First claim is that the kernel of phi is a congruence on X. The second claim is that the image of phi is a subset of Y. And the last claim is that the quotient of X modulo the kernel of phi is isomorphic to the image of phi. Proof: if R and T are two elements in X such that phi of R is equal to phi of T, then phi of A dot R is equal to A dot phi of R because phi is a homomorphism, which is equal to A dot phi of T because phi of R is equal to phi of T, and this is equal to phi of A dot T because phi is a homomorphism. And this exactly means that the kernel of phi is a congruence on X. So this proves claim A. Claim B we already proved, and claim C follows directly from the definitions. So this is the first isomorphism theorem for acts over semigroups. Finally, let us talk a little bit about the right action. So let S be a semigroup and X a set. Definition: a right action of S on X is a map from X times S to X, which sends the pair R, A to R dot A. So now here A acts on R on the right. And this should satisfy the conditions that R dot A dot B is equal to R dot AB for all AB in S and R in X. And as usual, this is an action by total transformations, the default meaning of the word action. Alternatively, we can describe it as a homomorphism from the opposite semigroup S-op to the full transformation semigroup Tx on X. And this sends an element A from S-op to the transformation blank dot A, so this is how A acts on an element of X. And this condition in the definition of the action is exactly equivalent to the fact that this is a homomorphism from the opposite semigroup. Acting first by A and then by B is the same as acting by AB, so it's an action on the right-hand side. For example, each S acts on any X trivially, where each element of S is realized as the identity transformation on X. So this is true both for the left and for the right action. And we also have the right regular action of S on itself, where each element A in S acts as multiplication with A on the right. So it sends R in S to RA. And we can also define partial acts. If a semigroup S acts on a set X by partial transformations, then X is called a partial S act. We can define homomorphisms of partial S acts similarly to the usual acts, but using partial maps between the sets. And the category of all partial S acts is denoted as P act. It has a subcategory in which homomorphisms are defined using total maps. And a right partial S act is given by a homomorphism from the opposite semigroup SOP to the semigroup PTX. And so we have the category of right partial S acts, which is denoted P act S, and the category of right S acts, which is denoted by act S. Some problems and questions at the end. Problem question 1. Let A be a set, an alphabet, and A star the set of all finite words over A. Show that the multiplicative semigroup of all positive integers acts on A star such that the integer k sends a word w to ww and so on repeated k times. So it repeats a word w k times. Problem question 2. Prove with all details that if phi is a homomorphism from an S act X to an S act Y, and psi is a homomorphism from Y to an S act Z, then psi after phi is a homomorphism from X to Z. Problem question 3. Prove in detail first isomorphism theorem. Problem question 4. Prove with all details that if Y is an invariant subset of an S act X, then rho Y defined via R and T are rho Y equivalent if and only if R is equal to T, or R and T belong to Y, is a congruence on X. And problem question 5. Check with all details that the quotient of an act by a congruence is an act. Thank you very much and see you next time.